All right, welcome back. I hope you're ready to talk some more linear regression today. Let's open a pizza joint. That sounds like some fun, right? I wouldn't lie if I told you that I have considered franchising a pizza joint at one point in my life. Not that long ago. Because I figure if I pay for it, then I can eat all the pizza I want. I thought better about it. It wasn't the best idea. But let's say we open a pizza joint, and I got a great name for it. We'll call it Best Fit Pizza. Why not, right? At Best Fit Pizza, you can get a plain pizza for $8. That's a heck of a deal. I don't think you can find too many pizzas for $8 anywhere nowadays. And you can get additional toppings for $1.50 each. There are a variety of toppings, they all cost $1.50. So, if you were to make a scatter plot where the horizontal axis, the explanatory variable, is the number of toppings, going from 0 to 4, let's say, and on the vertical axis, we have our response variable is the cost of the pizza, going from $8 up to $14, and we make a scatter plot, you see all those points line up perfectly on that line because a plain pizza with no toppings is $8, so 0 toppings, $8. That's this point right here. If you add a topping, you're at 1 topping, it's now $9.50. So our second point is here, still on the line. Every topping, you add $1.50. So, based on what we see in that scatter plot, I've got a question for you. Which of these two statements is correct? We've got statement A, the number of toppings explain 100% of the pizza's cost. Or B, the number of toppings explain 100% of the variation in pizza's cost. So, take a few seconds, think about that. Might even want to pause the video so I don't spoil it for you. Come back when you think you know which one it is. Got your answer? Let's say it's A. The number of toppings explain 100% of the pizza's cost. Well, here at Best Fit Pizza, we hire people to make our pizzas. The pizzas have dough in them, cheese, maybe there are toppings involved. Those people probably want to get paid to make the pizzas. I don't think they're going to want to work for free. Although if anyone wants to work at Best Fit Pizza for free, I would gladly hire them. Right? But there are a lot of things that go into the cost of the pizza. The rent for where the pizza joint is costs money, right? All of those things go into the pizza cost. So to say that 100% of the pizza's cost is based on toppings, that can't be right. Right? Only a small fraction of the pizza's cost is the number of toppings. And in fact, for a plain pizza, none of it is due to toppings because there aren't any. So it's not A. So what we're saying is B is correct. In that the number of toppings don't explain 100% of the pizza's cost, but they do explain 100% of the variation in pizza's cost. Why are these costs different? It's due to only the number of toppings. That is the only difference. Right? The only difference in how much a pizza costs at Best Fit Pizza is due to how many toppings there are. So it's explaining, the number of toppings are explaining 100% of the variation in costs, not 100% of the cost total. And that is a key distinction that we're going to want to make as we discuss something about linear regression we haven't talked about yet. And in order to get there, we need to go to a calculator. Okay, I lied. We don't need the calculator yet, but you can see it's ready to go. We're going to update the menu here at Best Fit Pizza. I've noticed, as the franchisee, that most people are getting their pizzas with toppings like pepperoni or sausage, right? And my profit margin on those toppings is a little lower because those are a little more expensive than the other types of toppings that we get. So charging $1.50 no matter what the topping is, I don't want to do that anymore. So now here at Best Fit Pizza, we offer 3 veggie toppings for only $1 each. Mushrooms, onions, and red peppers. And now we offer 2 premium toppings for $2 each, which is the pepperoni and the sausage, which cost more for me. So I want to pass that on to the consumers, but they don't know that. Okay? So by changing the menu in this way, pizzas are probably going to be a little more expensive for most people because they're going to want to get the premium toppings. And maybe everyone will have a little more money, except for the people buying the pizzas. So how does that affect the relationship between the number of toppings and the pizza's cost? Now that all the toppings aren't the same cost, I don't think it's going to look like this. So it might help to know what all the different possible combinations are for how many toppings we have and what the cost is. So let's make a table of those possibilities. So we've got the number of toppings versus cost. So maybe someone just wants a plain pizza, they don't want any toppings. That's still going to cost them $8, just like it used to. But if they want one topping on their pizza, there are 2 different options. They can go for one of the veggie toppings that costs $1 extra. That would make the pizza $9. But if the topping they want is one of the premium ones, that's going to be $2 plus the original 8, which is 10. So now, based on what type of topping it is, the cost of the pizza can be different. What if they want more toppings? If they want 2, there are actually 3 different ways you can get 2 toppings. They could both be veggie. 2 toppings that are both veggie would cost $1 each. That would be a total of 10. If they want one of each, that's going to be a total of $3 for the toppings, plus the 8 is 11. And if they want both of these, pepperoni and sausage, that's going to be $4 extra from the original 8, so that's 12. We can continue here. It turns out there's 3 different ways to get 3 toppings, and those would cost $11, $12, or $13. If you don't believe me how the rest of this is going, you can verify it on your own. It's not that difficult. For 4 toppings, that would cost either $13 or $14. And 5 is the most number of toppings you can order on a pizza because we only offer 5 total toppings. And if you get all of them, that's going to be a total of a $15 pizza. So we now have all of these possibilities for the number of toppings versus the cost. Time to bring this into play. What are we going to do with this data? Let's put it in L1 and L2. Yay! So, what I want you to do, enter this into L1 and L2, and go ahead and get a scatter plot of this data, and also run a linear regression. Run linreg and get that regression equation. Go ahead and do that. Pause the video, come back when you've got it, and we'll compare notes. We'll get to the linear regression in just a second. This is what your scatter plot should look like. If it looks like this, awesome. If not, you may have messed something up here. Let me show you what the regression equation looks like. This should be what the estimated regression line looks like. We've got our estimated cost. We're trying to estimate the cost of the pizza based on the number of toppings. 8.13 plus 1.35 times toppings. Now, one of those parameters makes some sense and the other one not so much. The one that might not make a whole lot of sense is actually the intercept, the y-intercept of this equation. 8.13 would represent if we got a pizza with no toppings, our model would predict that the pizza costs $8.13. We know that a plain pizza is $8. But the calculator doesn't know. It's never been to Best Fit Pizza. All it knows is this. And yes, there's a point at 0.8, but the line isn't necessarily going through that point. It's actually going to be a little higher. So it's not too far off. It's only 13 cents too high. But that intercept isn't exactly where it should be, based on what we know. Calculator doesn't know that, though. The slope is 135. So what this is saying is, for every additional topping that we put on the pizza, we would predict the pizza to cost $1.35 more. Is that reasonable? Yeah. I mean, it should definitely be between 1 and 2, right? Because some of the toppings cost $1 each, and some cost $2 each. And there are more $1 toppings than $2 toppings, so it makes sense that this is actually a little under 1.5. I think that's a pretty good model. Not too bad. But what I want to talk about also are the other numbers you see here. We've got our old friend R, the correlation coefficient. R is equal to, what does it say? 0.889. Okay. So based on the scatter plot that you saw a little bit earlier, we know that that's a linear relationship, right? It makes sense to fit a straight line to that. This is telling us that is a strong positive relationship between the number of toppings and how much a pizza costs. And that makes sense. We would expect a strong relationship between those two things. There is one other number on that screen, though. R squared is equal to 0.943. Again, if you're using the virtual calculator, you have to go to second catalog, that's second 0, and go to diagnostic on every time you use the calculator. If you've got your own personal calculator, you shouldn't have to do that every single time. That's how you get these on the screen. And that R squared, I wonder what that tells us. Are these backwards? They're backwards, aren't they? Why didn't anyone say anything? This is R squared, and this is R. Maybe you were yelling at your phone or your Chromebook or your computer the last 5 minutes. I'm sorry. This is R. This is R squared. For some reason, R squared is the number on top. I wish it would put R first. Anyway, this is R squared. It turns out the R squared value tells us what percent of the variation in Y X can predict. So let's write that out. First of all, R squared, it's usually denoted with a capital R. The calculator has it as a lowercase, but we usually give it a capital R. R squared, it's called the coefficient of determination. So R is the correlation coefficient, and R squared is the coefficient of determination. It's very determined, I guess. The way you calculate R squared is actually quite simple. You take R and you square it. So R squared is equal to R, whatever R is, squared. Super simple. That's exactly why it's called R squared. Awesome. So what that means, before we get to the interpretation again, which I already said, the bounds on R squared, if it's R squared and R is something between -1 and 1, then what are the bounds on r squared? What's the smallest it can be? 0, right? You can't get something squared and have it be negative. So 0 is the lowest it can be. And what's the biggest that r squared could be? 1. Okay. So r has to be between -1 and 1. So when you square that, r squared has to be between 0 and 1. It could be equal to 0 or equal to 1. If r is 0, r squared is going to be 0. If r is -1 or +1, if you square either of those numbers, you get 1. Or it could be anything in between. The closer r squared is to 1, the more variability x is explaining. So, interpreting r squared. Interpreting r squared. And again, hopefully this is all going in your notes. If I write something here, it's probably important enough for you to put in your notes. I don't write everything. You might want to be writing down things that I'm saying that I'm not writing down. I'm also trying to conserve board space because I don't want to have to erase everything during the video. So, to interpret this value, we say that the variable x, whatever it represents, sorry, I'm not very good with my eyes, much better. X explains approximately. X explains approximately and then you will report r squared as a percentage, right? So r squared, from your calculator, it gives it to you as a decimal. We will always report r squared as a percentage. So this is really 88.9%. So that's how we would report it in our interpretation. Okay, so whatever r squared is as a percent, of the variation in y, whatever y happens to be. So, let's see how that plays out when we put it in the context of what we just did with our pizzas. Let's interpret this r squared value. Well, x, the variable x, is going to be the number of toppings. It's our explanatory variable, right? You can find it here in your model. You can find it on the horizontal axis if you've made a scatter plot. So the number of toppings explains approximately r squared as a percentage, 88.9% of the variation in pizza cost. That's why. Number of toppings explains approximately 88.9% of the variation in pizza cost. All right. But I thought toppings explained 100% of the variation in pizza cost. That was when all the toppings cost the same amount. Now that our toppings cost different amounts of money, pizza cost isn't entirely explained by the number of toppings anymore. What else is explaining the variation in pizza cost here? Not the number of toppings alone, but also which type of topping. So that might be the other 11.1%, right? It's not a straight line anymore on that scatter plot. There's some variability there. And that variability is also due to the type of topping, not just the number of them. All right, so now we know about r squared. We're filling in all the holes. We now know what all of these things mean. R squared Anytime you run a linear regression, you will get a value for r, you will get a value for r squared. But just like when we were talking about r, it's only valid if you've got a linear relationship. Don't go interpreting r squared if you don't know if there's a linear relationship. You would need to look at that scatter plot or be told in the problem that the relationship is linear before you can make this statement. You're going to look really silly saying this if the relationship is like curved or something, because r squared is meaningless. It's also a measure of variation explained in a linear relationship only. Okay. Let's see, what are we going to do now? What are we going to do? Okay, so we know how, we're not going to do it for this example, but we know how to predict a pizza's cost for any number of toppings, okay? What we would predict the pizza to cost. So if we plugged in 2 here, how much would the model predict a 2-topping pizza to cost? Whatever, we would plug in 2 here and we would get our cost. What if I wanted to predict the number of toppings on a pizza given how much the pizza costs? How about that? What I'm saying is I want to take the hat and put it on toppings instead. So if I knew I wanted a pizza that cost $10 and I wanted to know how many toppings I could get on that pizza, could I plug in 10 here and try and predict the number of toppings? Can I do that? Can I just take this hat and go, boop? No, that is not allowed. This model is assuming that this is the explanatory variable and this is the response variable. In order to flip those roles and put the hat here, you would have to take this scatter plot and invert the axes. On your calculator, you would have to do linreg xlist is y2 and ywist, the ywist is L1. The ylist would be L1. You would have to tell it the other way around. This doesn't work if you want to predict toppings based on cost. Okay, that hat can't just move from here to here. You would have to start over and do the linear regression using this as x and this as y. Okay, so you might be tempted by a problem to try and solve for toppings given cost. Using this equation, you cannot do that. That's called back solving, and it's bad. And it's even worse the lower this value is. You'll actually find, since this is a relatively high r squared, if you tried predicting toppings from cost using this, the values you would get would be pretty similar, whether you did it using this formula or whether you did the linear regression with the variables reversed. But that's a bad idea. Don't ever do that. Please don't ever do that. You'd have to run the regression again with the variables backwards. Okay, so let me get an example up here and we'll work through it. Okay, so my apologies. You probably looked at the length of this video and you're saying, what the heck is Mr. C doing? I figured it was better to do it all in one video than to split it up into 2 pieces. And tomorrow, or the next e-learning day, I don't know which day this is for, you'll just be taking a quiz over the Chapter 7 material from the last few videos. So if you want to watch this the next day, break it up into 2 pieces, you can do that. But tomorrow is just a quiz. That shouldn't take very long. I want to go through the example based on this. And what you're seeing here, right next to my hand, is a scatter plot detailing the foot length in centimeters versus height in centimeters for 15 high school students. So the first graph here is a scatter plot, and you could describe the relationship between those variables. I didn't ask you to do that here. To the right of that, you see the residual plot So you've still got foot length on that horizontal axis, but on the vertical axis, you've got the residuals. And here on the bottom, you see something you haven't seen before. And on most problems, on tests or quizzes or the AP test, you're not going to be given the raw data and be expected to do the linreg on your own. It'll be done for you. And that's what this represents. It is output if you do a linear regression using computer software. So, as part of this example, we'll teach you how to read this, what information it gives you, and you'll be very comfortable with it once we're done. But let's start here. Is this a linear regression model? Yes. Is a linear regression model appropriate for this data? Explain. It's a skill that you'll learn in this class, that when you see a question, you kind of have to know what it wants you to do. Because this is not asking for your opinion. There's a very specific way to determine if a linear model is appropriate. And it involves looking at this graph, the residual plot. That residual plot will tell you whether a linear model is appropriate. What is it we're looking for in the residuals? Random scatter. Is that what we see in that residual plot? Is there really any kind of relationship in those points? No. It looks like someone shot a shotgun and everything just scattered on that graph. That is perfectly exactly what we want to see. So the answer is yes. Yes, because there is random scatter. Among the residuals in the residual plot. It's exactly what we want to see. That means it's appropriate. If we had seen some kind of like curved relationship in that residual plot, or if we saw like a fan shape like we've seen in the past, that would give us pause here, and we might say that it's not appropriate to do linear regression. But if there's random scatter, we're good to go. Part B, determine the linear model. Now, this is going to be very difficult to do using the graphs. We're going to have to interpret this output. So, we can see down there it says predictor, constant, and foot length. And across those columns it has coef, SE coef, T, and P. The only things that you need to look at to answer this question and determine what the model looks like are the names on the left-hand side, constant and foot length, and the numbers under coef. Those are the only two things you need to answer this. We know, without even looking at that output, we know that the model is trying to predict the height, right? Because that's what's on the y-axis. We're trying to predict height. The variable on the y-axis is going to be equal to something, and then something times the explanatory variable, the x variable, which is foot length. So at the very least, we can write that part. Now, what's the y-intercept and what's the slope? We've got to interpret that here. Where it says constant, that's going to be our y-intercept. And it's a constant because it doesn't have a variable attached to it, right? It's just the number itself. And that constant is under coef, and it's 103.41. 103.41. Okay. And the slope is going to be with foot length. So where it says foot length, that coef, or that coefficient for the slope is going to be 2.75. 2.75. Positive 2.75. Okay. And we know that that should be a positive number because if we look at the scatter plot, the slope of that line is in fact positive. It's going up to the right. So this is our model. And that is how you read the table to determine it. Not bad, huh? We don't need to know SE coef, T, or P yet. By the time you're through with this course, you will intimately understand everything in that table. But for now, that's all you need. C. Interpret the slope and the y-intercept in context. So based on the variables that we know, which are already here because we wrote this correctly, interpret the slope and y-intercept. You might want to pause this video and do that on your own. Make sure you get it right so that when you come back, you can check your answer. Okay, there are my interpretations for the slope and y-intercept. Slope first. For every additional centimeter of foot length, our x variable, a student's height, the y variable, is predicted to increase by 2.5 centimeters on average. I want to point out where many students falter in interpreting the slope of a best fit line. If you don't have either of these phrases or something similar to it, your interpretation is wrong. If you said for every additional centimeter of foot length, a student's height will increase by 2.5 centimeters, that's not true. That would only be the case if there was no variability in that data and all the points were on the line. Since there is that variability, you have to say something like predicted or estimated or something like that. Or you could put on average. You don't need both of these, but I put them there because I'm super skeptical. And it's not wrong to put them both. But you need at least some fudge phrase. Because if you say a student's height will increase by 2.75 centimeters, that is wrong. That is an incorrect understanding of the slope of that line. So make sure you include some kind of fudge word or phrase in there. For the y-intercept, for a student with a foot length of 0 centimeters, we predict a height of 103.41 centimeters. So it turns out if your feet have no length, you are predicted to be about a centimeter, or a little over a meter tall. Does that make sense? No. I obviously not, right? But that is the interpretation of the slope. When x is 0, what do we predict y to be? Well, it's going to be the y-intercept. All right. So part D, let's see here. We are interpreting the coefficient of determination in context. In order to interpret it, we have to know what it is first. So what was the coefficient of determination again? That's r squared. And here r squared is, we go back to our table here, and it says r-sq there at the bottom, in the middle. r-sq, that's r squared, equals 48.6%. So this output is already smarter than our graphing calculator because it outputs r squared as a percentage, which is how we want it. How do we interpret that? Well, let's use the same template that we used earlier in the video to describe r squared. Let's see. Okay, so the x variable first, a student's foot length, explains approximately 48.6% of the variation in a student's height. So a student's foot length explains approximately 48.6% of the variation in a student's height. So a little less than half of that variability is explained just by foot length. There are other things involved, but this model is only accounting for foot length's effect on height. There are other things, but 48.6% for this. Okay, so what is the value of the correlation coefficient? So we talked about how to get r squared from r. But you'll notice in our output here, we don't have r. We only have r squared. But if we square r to get r squared, and we have r squared, how do we get r? We take the square root. I love math. So r is equal to the square root of r squared. So that's going to be the square root of 0.486. Remember to turn that back into a decimal before you take the square root. If you do 48.6 here, that's going to be a bad time. So that's going to be 0.697. Okay. So it's important to know that you can go either way there, right? You can get r from r squared, you can get r squared from r. You just have to know whether to square or take the square root. And it depends on what you start with. So here's the question about something like this. We said r could be negative, right? It's possible for r to be anything as low as -1. But by doing this calculation, r is always going to be positive. So how could you possibly get a negative value for r? It's a great question. You will always calculate r this way if what you have is r squared. You will take the square root. Your r will have to be negative once you're done if in the scatter plot you see that the relationship is negative in slope. Or if you have created your model and the slope is negative, that tells you that the correlation needs to be negative as well. Okay? So by doing this calculation, r will always be positive, but you need to take a look at either your regression equation or the scatter plot. And if you see a negative slope, you need to change this to be negative. That's the only way to get it. All right. So there is also one other value of interest in this table down here, and it's right there. It says S equals 7.98 or something like that. S equals 7.95. S is the standard deviation of the residuals. Okay. Remember how we can calculate the residual for each of the points on that scatter plot by taking the vertical distance between the point and the line? Well, if we get the residual for every point, we can take the standard deviation of them. That is S. The interpretation of S is it's the typical distance between the observed and predicted values of y. It's the typical distance between the observed and predicted values of y. It doesn't come up all that often, but you might have a homework question that asks something about S, and you may see it on a quiz or a test. That's all you'll need to know, is that it's the typical distance between the observed and predicted values of y. Right? That's essentially the typical residual. Okay? It's not the mean residual because that's 0, but it's the typical distance between any random point and the line. All right, so again, I apologize for this very, very lengthy video. You can split it into 2 pieces if you want. It's a lot of material, and I apologize. You've got homework over the Chapter 7 material in the textbooks, so make sure you do those problems. Those will be due in a couple days. And you will also have a quiz over just the Chapter 7 material. And again, I usually give quizzes over material I think is important. All of this linear regression related stuff is going to come back later. So it's important that you know it cold, so that even if it slips and you forget it later, you have a base to go back to when we get back to it later in the year. So, for now, thank you for watching this very long video. If you made it to the end, woo! Celebrate. Hopefully you took good notes so you'll not have to watch it again. And we'll see you in the next video.